Okay, now I have started recording the session. So what is this is about this is extension of chapter number uh, 7. This is about sampling, distribution and estimation. So this is very important topic to be understood properly. So sampling estimation, so we are just going to, this is also starting of the inferential statistics. Inferential statistics means based on the sample, how we can you know uh, inference about population. So this is, so sample statistics is a random variable whose value depends on which population item are included in the random sample. So let's say I'm doing a study of Eastern Washington University, and it sample it depends on the item that I have taken from the Eastern Washington University students. The sample size also, sample statistics could either represent the population well or could differ greatly from the population in case of sample sizes is small. So, for example, if I take randomly 500 student sample, and I will conclude something that based on my 500 sample, I will say Eastern Washington University students average age is 22 years, or average CGPA is is like 3.8. But I have not collected all 12-13,000 students based on only 500 students. But instead of 500 students, if I go and do like 50 students in my class, like I'm doing any undergraduate class, will that be sufficient to represent all 13,000 students of Eastern Washington? So basically, this is starting of the inferential statistics. Sample variation can easily be illustrated by selecting random sample from large population. Bigger is the sample size, is better is the you know inference. So uh, consider the sampling of a large population of geomet score of MB applicant. The population parameters are this, and sigma is this, mu is this, sigma is this. So here large population, mu is this, sigma is this. And if you do this multiple time, for example, if you take these samples, n equal 8 samples of n equal to 5. So let me explain in my graph, my whiteboard, this concept, because this explains this is most important concept to be. Okay, so now here we can see, let's see, this is a normal distribution. For example, this is a population. So let's say I have 13,000 students with Eastern Washington University, total n equal to 13,000 with EWU. Let's say I'm just taking a sample of 500 each time. So my sample n equal to 500. So first sample I got, and I got, for example, the sample mean is here, and the confidence interval is like this. Their upper and lower limits are like this. What are those? I'm just going to, so this is for first sample. let's say second sample, this mean is here. This is, you know, so this sample is representing the population mean, which is right here. This sample is also representing because you know upper and lower. I took third sample, which means is going to be here, and their plus minus point is going here. Similarly, I do, you know, like 10 samples. This is, these are three. This is, for example, this sample mean is this. Mean is this, you know, the dark point, and this is this. So 4. I do fifth here, and that goes here. Let's say I'm just doing, assume I'm just doing 10. Out of 10, 9 of them representing the true population mean, and one is not representing, because you know that, you know, this is population mean. From this population, I draw these 10 and 10 times. Out of 10 samples, 9 are representing the true population mean, which is, you know, with a university IT or university, you know, grade or something, I can get to know this is a true population mean. And when I see, so 9 out of 10, this says 90% confidence. What it says, this is the meaning of 90% confidence. I will represent in this way. I will say this statement in this way. I'm 90% confident that the sample will represent the population mean. I'm still 10% not confident because this incident happened. So still I'm not 10%. Still the risk is there that, you know, whatever sample I will take from the students, 500 students of EWU, that may not represent the true population mean. Means out of 10, let's say I'm doing any population, I'm doing like 100 times, I'm doing this exercise from any population, and my 99 samples are representing true population mean, one is not, then I can say I'm 99% confident that, you know, the sample is representing the true population mean. Out of 100, if 95 are representing, then I will say 95% confident. If out of 100, 90 are representing, 10 are not representing, what is the meaning of all, you know, this is still, you know, I have a risk that, you know, out of 100, one sample will not represent the true population. This is a probability, this is a statistic, so we can understand that certainly we can't be 100% sure about anything. Therefore, there is a 90% confidence, 10% non-confidence or not confident or risk or whatever you say. So the same thing, you know, sample. So I just, you know, so when we take the samples, we represent about, we take the samples and we infer about population. So sample mean is represented by X bar formula. Parameter is about population, and these are about, this is called statistics, which is based on sample, and these are called parameters. So X bar mu, small p pi, small s sigma. Sampling error. So, you know, just let's go, you know, as you go, you know, higher sample size, n equal to 5, n equal to 20, n equal to, you know, the distribution becomes, you know, normal. Central limit theorem, we are just, you know, so normal and sample mean. So as you go higher, you know, in n equal to 1, 2, 3, 4, the distribution becomes symmetric, it becomes normal. All distribution, uniform, normal, triangular, is all distribution follow the normal bell-shaped curve, which you can see here. So central limit theorem, this is, now expected range of sample means. What is the range? Mu, so there are applying central limit theorem. Mu is a population mean plus 1 minus 645 sigma divided by square root of n. 90% inter 95%, this is 90%, this is 95, this is 99. So the value of 95% are, so I can demonstrate one more time, how we take. So I just go here, graph probability distribution, and so normal.
We're not seeing your screen, or at least I'm not.
Oh, just a minute. Oh, I'm sorry. Oh, it happens when you. Okay, let me go through this. Oh, sorry, Chris. Let me go back and. So yeah, this is now. I hope you can see it. Even I didn't see your chat. So
yeah, we can see it now.
So I'm just repeating it again. So this is a population. This is a sample or estimators. So you can clearly see in this population parameters are represented by mu, sigma, pi. Here we represent x bar, s, and pi is p here, sigma is s here, mu is x bar is here. So this is for population, this is for sample. So what we do, we take the sample because practically we can't take all the items in the population. And let's say we are going to do any behavioral study of Eastern Washington University. I hope at a one time we can't get all 13,000 students or whatever number of students we have. So we go and get the sample, and based on a sample, we represent Eastern Washington University. Okay, this is the behavior of Eastern Washington. We don't say in our conclusion, this is the behavior of 500 sample students in our study. We always say, this is the behavior of Eastern Washington University as a whole, based on only 500 samples. Like, I gave the example, if we have any problem, we have 7 liter blood in our body. So what, lab person or, the test person, he takes only 5 ml from our body. And based on 5 ml, he does, all the test and find the problem. And what doctor does or, physician does, he prescribed the medicine for entire 7 liter to be, or for entire body based on only 5 ml sample. So exactly the same thing we are doing here. We are just taking only, sufficient number that I will explain in next, thing. So as you go on, and if your sample size is larger or bigger, n equal to 520, you can see the shape of the distribution. It becomes more and more symmetric and normal. And so this is what I was saying. If you have high, if sample is large enough, every distribution, uniform, triangular, normal, skewed, whatever you have, everything will follow the bell-shaped or normal distribution. So every distribution will convert into this form. And yeah, so 90% interval, 95%, 99%. So how do we get 1.645, 1.96? I'm just going to demonstrate, then I'm going to show you. So here, yeah, this is, I hope you can see my Minitab you can see. And now, standard deviation in 1, and this is always 0. Now I'm going to do this. I'm going to see, I want 95%. So, or 0.9 first. So this is for 90%. I did the wrong thing. Probability distribution. Okay. And I have to do this instead of that 1% here because it, yeah. So can you see this minus 1.64 plus 1.64? Similarly, so here you can see 90%, 1.64. So plus minus, you can see the numbers. Similarly, you can see for 95%. Okay, 95%. So I will put here 5% only. I think I selected again a wrong thing. Probability distribution, and okay, here we go. Oh, I selected 50%. I have to put 0.5. Yeah, so you can see minus 1.96 plus 1.96. So for 90%, you can 95, you can see 1 point. Similarly, for 99%, graph probability distribution, and okay, and here we do, and 99. So I just go with 1% here. Now I think I selected the correct one. And here you can see minus 2.576 plus 2.576. So this is the expected range of sample means with 90% interval, 95%, 99. So mu is a population mean plus minus 2.567 or whatever number, 90 sigma square root of n. So a standard, this part, sigma divided by square root of n. So this is a z value of a standard normal distribution, which we just have seen. If we know mu, sigma, and so this can predict the range of sample mean or sample for sample size n. If sample size is n, then you can see sigma upon square root is called standard error. So if n equal to 4, what is the standard error? Sigma upon 2. If n equal to 16, sigma upon 4. If n equal to 64, sigma upon 8. Means the denominator or bottom value is going to be increased, and the overall this part, overall this standard error part is going to decrease or going to get minimized. So the higher the sample size is better the better is the range that you can consistency in the range you can observe. So let's say I'm just going to go directly on confidence interval. So x bar, so how do we get the confidence interval for a mean mu with known sigma? There are two things, which is known sigma and unknown sigma. Now I come on the direct example. This is a practical thing. So, and real data that, every year almost 300,000 overseas students come to United States, 300,000. Out of which 22,000, 23,000 students are from India. They come every year. And, even United States USCIS, Citizenship and Immigration Services, which issues the visa, they don't record the information about what is their GRE score, what is their TOEFL score, what university they are applying, what is their CGPA. They don't look into all these matters. They look into different in order to issue visa. So I would like to know, what is the all students coming to in USA, what is their average CGPA, what is their average GRE, all 22,000 students. However, it's difficult for me to collect the information, because some students may drop, some student may go, some student may come, some are not available for me to give the. So it is very difficult. Even Indian embassy does not have all the data. US embassy doesn't have all this. What I can do? So getting 22,000 student average, GRE score, TOEFL score, CGPA, research, and all is very difficult for me. So what I have done, okay, whoever is available, let me get the sample, random sample of 500 students. So this is the real data of 500 students I collected. Okay. Now based on that, can I say about these 22,000 students? All the students, those who are coming with from India, what is their CGPA? So sample mean I can get, but I cannot get exactly, the all the students, those are coming from India, their average CGPA would be like 8.9. No, I cannot get the answer exactly, but I can get the answer. It would be between 8.5 to 8.9 with 95 per, sorry, 8.9. You can understand this is 89 is 8.9. So I can find the range. I can find the range that. So let me do this example. So I go under this statistics. I have basic statistics, one sample t-test. I'm just going to use, this one sample. So I'm just going to do ZRE, let's say ZRE, and select this. I have option at what percent of confidence I would like to say 95%, or let me do this. Now here we can see, if you can see the answer here, I am 95% confidence. Here, can you see this? All 22,000, all 22,000 students coming from India, their CGPA will be between 3.15, 300, I mean roughly taking, 315.5 to 317.5. I'm 95% confidence. That means still I have 5%, because based on this sample, maybe I have collected such a sample which does not represent the true population. So with 95%, suppose I would like to increase this 95% confidence, I would like to increase my confidence level, then what would be? I can give the bigger range here. So let's say I'm just going to do this from 95 to 99. The range will be bigger. So let's say statistics, basic statistics, one sample T, and here I'm just choosing 99 option. Here, what was the range here? 315.48 to 317. Now look into this. 315.166 to 317. So, few decimal points have been increased in both the side. Now I am 99% confidence. The true population mean of all, true population GRE score of all 22,000 students coming from India will be between 315.166 to 317.778. Now I do the same thing. If I take 90%, if I'm taking the 90%, this will be narrower, because I am just taking a more chance, more risk, 10% risk. Here only 1% risk is there. Therefore, this is distance, or the uh, confidence interval is bigger. Let me do this for 90%. Where am I? So let me do this with 90%. Hopefully, look into that. The range has been reduced. In 95, it was 315.5 to 317.5. Now the range has been reduced. but I am taking at the same time, I'm taking 10% risk, higher risk. So if you give, higher risk, you will have narrower distance or small confidence interval. If you have higher, confidence interval, you will have, bigger range. So this is, if you understand this, I'm going to move further. So this is the confidence interval that you can see in the picture. What is the confidence interval? Look into this. The mu, that this is true population. Mu represent the population mean. X bar means sample mean minus z alpha by 2 that we can get, from table, like we did for 90%, 90 plus minus 1 point. Sigma is population standard deviation. If you know the population standard deviation, that is for sigma. Square root of n means sample size. So this is once a time we subtract this to get this side value. So one time we subtract to get left side. One time we add and we get this. So what is the important role here? The sample mean, the population standard deviation, and sample size, all three play. If sample size is large enough, this quantity becomes very small, and you have very, small range or a small confidence interval in which you can say the true population will be based on that. So is it making sense? So this is a confidence interval here, you can say. If it is making sense, I can go ahead. Now there are three cases. For example, you make, bigger confidence. This slide explains you 99% it is bigger range, 95 is smaller, medium, and 90 is lower. So higher confidence level leads to wider confidence interval. Greater confidence imply loss of precision, means, you have the risk, greater margin of error. So now there are three cases. One is mu, confidence interval for mean when sigma is known. Mu with sigma is known. So this comes under Z test, and that case a confidence interval either does or does not contain mu. Like I said, 90% contains, 5% 10% chance does not contain. So this is the meaning. Out of 100 confidence interval, approximately 95 may contain mu, while approximately 5% might not contain mu when constructing 95% confidence interval. So like I demonstrated exactly the same things in wording here. Is it clear to everyone? If it is clear, because this is the most important concept, what is the meaning of confidence interval? When we can assume normality, here is the concept. N must be greater than or equal to 30, then only we can assume. This is, statistics rule. Like you remember, you saw the T table, with 30 n equal to 30 plus the, T value, and, infinite value of Z table and T table, they are coming close, very close. So the rule of thumb is n equal to greater than or equal to 30 is the case. So, there are three cases. Number one is when sigma is given, means population standard deviation is given. When we don't have population standard deviation, we use student t distribution, which is this. So x bar equal to plus minus So this is, sample mean. You can simply understand x bar is sample mean plus minus t value. S small s is sample standard deviation, or square root of n is again sample size. Based on that, you calculate confidence interval. So here T and T, and you can do this exactly same. Only the option is here. If you look into my here stat, and under stat basic statistics, here you have one sample z test, one sample t test. Look into one sample z test. So here it is asking known standard. I don't know the population standard deviation, so I can't take the z test. If I know the total all 22,000 Indian students standard deviation of z, then I can use the z test. Otherwise, what am I going to do? Statistics, basic, and t test. So because it does not ask the confidence, the standard deviation, automatically it calculates from the sample. So this is student t distribution. Degree of freedom. What is the degree of freedom? N is the sample size minus 1, that is a degree of freedom. So like if you have 31 sample, 31 minus 1, degree of freedom would be 30. So this is how you can do degree of freedom. Means sample size minus 1. GNT test, for example, n equal to 31, the degree of freedom would be 30. So for 90% confidence interval, we would use T, which is, which is only slightly higher than Z value, which is 1.645. So this is what we have seen in previous class, that, after n equal to 30, these values are very close to each other. So ZMAT, like, this is ZMAT. So we are doing for ZRE. Construct 90% confidence for mean ZMAT score of all MBA, where X bar is equal to this much, S equal to this much. So we can also do, we are not going to use any. Here we can use summarized data. What is the sample size? 20 minus 1, which is, so sample size is 20. So we are going to do sample size 20. Sample mean is 510. Sample standard deviation is 73.77. And 90%, or what it is asking, 90%. So this is 90%. And 481.5 to 538.5. So if you don't use this, if you have summarized data, mean and standard deviation and sample size, you can also put in the, this, and you can get the 481 to 538. Let's see. So we are not looking into this. So 500, so this value is coming 510 plus 20, So you can see this is the, instead of doing 481.48 to 538 point, this is the answer. This is the table, classical way. When I used to use these kind of book table, but you have all the facility of, software. So this is lower limit. So I'm 90% confident that true mean of GMAT score within the interval of 481.48 to this much. Is it making sense?
This part's not making it sense to me. Could we try one more time?
Oh yeah. So what is the, let's say, you have a, sample, you want to see the entire GMAT students average. What is the entire student GMAT score? Okay, you took the sample of 20 students. So you took a 20 student sample, and you find the average is coming of based on sample 510. The standard deviation is coming 73 point, and the sample size is 20. Okay. Now you are interested to know what is the all student GMAT score, average or average of all student GMAT score. How we can do? Here we have sample standard deviation, we have sample. So we are going to use which test we are going to use, which one sample t-test. When sigma means population standard deviation. If that is given, we use z-test. When population standard deviation is not given, we use this. So I just took sample size is 20. Sample mean is 510, standard deviation. So there are two ways to do that. One, you can just, you have the all 20 students data in this Excel kind of sheet, or in sheet, then you can just use the, select the, from the column. But we have just summarized data, so we are just, and we are checking at 90%. Okay. So now we get the range. Here you can see. Now we are 90% confidence the true GMAT score will be between 481.5 to 538.5. So here the same thing it is, so example GMAT scores. So I'm not, putting all these things because we can get all the numbers in Minitab. So the 90% confidence interval is, so this calculation is automatically coming in our Minitab. You can understand this. We are 90% confident that the true mean GMAT score is within the interval 481.48 to 538.52. If we wanted a narrower interval within the same level of confidence, we would need a larger sample size to reduce the right hand side. So basically, if you want, this is 481 to 538 based on 20 sample size. So the range is very high, which is almost 18.5 here and 538 is here. So which is 38 plus 18, which is almost 54. 54, 55. Suppose you want to reduce this, you need to increase the sample size. You need to have 200 students, 300, then you can reduce the right hand size of this. So what makes your right hand size? This mean remains same. Mean can be, this n, if you have larger n, this total size will be reduced. Is it making sense now? Is it clear? If not, I can go again.
Nope, that's okay. Thank you.
You're welcome. So basically what this is inferential statistics. So based on sample, we inference about population. So let me do this. So, but so, again, confidence interval width depends on the, level. If you have narrower confidence level, you have narrower width. So I'm just going to, so one is about, here you can go. Same thing is about, sample size. Confidence interval for proportion, pi. Proportion, a proportion is a mean of data whose values are 0 or 1. So a sample size increases, the distribution of sample proportion approaches a normal distribution with mean. So this is the sigma p. Here, this is the formula. You don't need to remember the formulas. I'm just going to give you this is the must condition. When do we use the normal distribution? N pi is greater than 10 and 1 minus pi is greater than 10, that you have observed in, previous class. So these are the pi n value and corresponding pi's. So I'm just going to directly use, if you have proportion where 0, 1 case or male, female case, yes, no case, this is the confidence interval that you can see. So P plus minus Z alpha P1 minus P divided by N. So this is the formula. Now where we can use, look into this case. Here this is not continuous. This is research university and non-research university. So our university Eastern is not research university, teaching university. So teaching is 0. 1 is for research university. So this is all students information. Now I would like to see you, based on this 500 students, what is the true proportion of research university students, all 22,000. So I just go stat, basic statistics, and here we have one proportion, and I can select directly a column which is research column. Again, option 95, 90%. By default, everything comes 95. So you can do. Now here you can see. If you can see that this sample mean, here 500 students, out of which 56% are applying for research university. 56% means 280 out of 500. Okay. Now, if I take the entire, if I talk about entire 22,000 students where they are applying. So out of 22,000, 51, I'm 95% confident that 51.5% to 60.4%, true population mean, sorry, all, 51.5 to 60.4 will be applying to research university. So the research university application, I'm 95% confidence between 51.5 to 60.4. So measure of students. So this is my confidence based on proportion. So this is for proportion. Now, example of auditing. This is a sample of 75 retail in store purchase, so 24 were paid in cash. We will construct 95 confidence level. So, what is the probability of this proportion? 24 divided by 75, which is 0.35, 0.32, sorry. Now, we do the all calculation. P is 0.32. Z value is 95% is 1.960. Square root of 0.32, 1 minus 0.32 divided by 75. If we do all this calculation, clear. So we do all the calculation. We get 0.32 plus minus point, which is 0.214 to 0.26, 0.426. Same example, if suppose I would like to do for my mini tab, I just go here, stat, basic, one proportion, and I take summarize data. Number of events are 24. What is the number of trials that total done? 75. So you have to put only these two data. 95 is automatically. And now look into this. 2.16 to 4.437. And we get exactly 0.214 to 4.426. So this is confidence interval for a proportion. Now here you can see, now if finite sample is there, a finite population is there. For finite population, this is n, capital N is for population, small n for sample. This factor has been included in all the formulas. Here you can see this. This is added here in, this is z test, this is t, this is in proportion, this is added, and this is called finite population correction factor. That is population size minus sample size divided by population minus 1 and whole square root. This is called finite population correction factor. So suppose you have, we know Eastern has 13,000 students and we are taking 500 students out of that. Then we are going to use these situations. In this situation, we don't have, minitab option where we can put, finite population. We can put finite population number. So this is for your understanding. If this is making sense. So this has been added with each calculation. If you do this, if you have known the population and sample. Now, most important question is there. Most people ask, what about, if suppose I am going to do a research with Eastern Washington University students' buying behavior, what should be the sample size I need to have to do that? What should be the sample size I would like to have? 400 is sufficient, 500 is sufficient, 600 is sufficient. And that can be answered using this formula. So, this is the formula which is so as this is the second part, here mean plus z sigma square root of n. So this is called error part, or the estimation population mean with precision allowable error. So error is z sigma upon square root of n. Then we do the square root of both sides, and based on that, we come to the formula which is n equal to this much. So n can be written in this form: n equal to z sigma upon e square, or sample size to estimate mu. So here this is always round n to next higher integer to be conservative. Why? Because sample size cannot be 40.7 or 30.2. So if you are getting calculation 32.2, you just round up to 33. So always integer, always make this sample size as an integer. How do we get these values of ease, sigma, and all? So here are the methods to do that. Sigma is, very simple. 6 sigma is the range. 6 sigma is range. Therefore, based on sigma equal to highest value minus lowest value. So I'm just going to, so highest value minus lowest value divided by 6. So this is the way you can get the sigma, because range is 6 sigma. You can assume uniform population. In that case, sigma equal to this formula: highest range divided by lowest divided by 12, and then square root of this. Or first method that normally we do a pilot study, take a preliminary sample, take a small preliminary sample, and use the sample sigma in place of population sigma. So normally, if I want to do a big study, related to Eastern Washington University students' buying behavior, I will go first to take like 40-50 students pilot sample. Based on that, I can calculate S and all, and that I can replace, and I can get the sample size in my in my sample size calculation. In a special can, so many people, they do first pilot study, and based on that they decide the sample size. Sigma is also in Poisson interval. This is to do. So basically this I normally do normal, or do a pilot study. And here we have to estimate a population proportion with a precision of, you would need a sample of size, since sigma pi is number between error is between 0 and 1. So normally we do 50-50 in this case. Here it is, you can look into this case. Suppose we wish to estimate the population proportion with precision. This plus minus, this is a general form, and this is what we want. So basically these are the formulas, and in questions you get the what is the error term, what is the proportion, and how much sample size do we need. So for proportion, this is n equal to z upon e square and pi 1 minus. This is the formula. And always round to next highest integer. How to estimate pi? Normally 50-50%, normally this is the assumption people do in order to do the pi. They consider 50%. Let's say I'm going to do 50% students in Eastern Washington are having iPhone, 50% non-iPhone. 13,000. Yeah, that would be the possible. Or if you are taking bigger, study or something, always consider 50%. This is the assumption that we do. And so, this is about sample size. How do we get the sample size? How do we calculate? So here we go in. Under this, we have the option under power and sample size. So here we can do sample size estimation. So a standard error that we can get, or estimation from margin of error. These are the two options. So basically, these are determined based on so a standard deviation based on standard deviation, based on variance, based on proportion, based on mean, based on. So let's say we do standard. What is the standard deviation? So here we have other options, two side 90%. And we have one more options. So do we have example here? So if we take, any example that is in book, we can do this. So I'm just going to pull out a book and I'm going to demonstrate one example. So here, so I'm just looking on the page number 323. And the question says, a produce manager wants to estimate the mean weight of a Spanish onion being delivered by a supplier with 95% confidence. Error is plus minus 1 ounce. A preliminary sample of 12 onion shows a sample standard deviation 3.6 ounce. For 95% confidence, we will set z equal to, we use s equal to and e equal to 1. So what would be the sample size? So a standard deviation here 3.6, that 3.6. Margin of error is 1. Oh, stat sample size about, just a minute, I'm using. 3.6. Estimate sample size. Margin for error for confidence interval is 1. So the sample size here, for standard deviation 3.6, confidence interval 95, and margin of error 1, the sample size would be 42. 42 would be sufficient to do this, Similarly, another example, we would round to, so normally, some calculations are, you can see in this software 42, some other software, something different. You can do manual calculation, you will find little difference also. So you can, use the method stat, power, and sample size for estimate. Here you have the standard deviation. You have estimate sample size. So I was just doing a wrong. Estimate sample size. What is the margin of error? You can do, for example, standard deviation of the age of university students in Eastern Washington is, let's say, 2, or let's say 3. And margin of error is, let's say, 2. So here in this case, it is coming only sample size 30. So based on, preliminary or pilot study or pilot, you can get to know standard error, and then you can come to the sample size for estimation. So this is about chapter number 8. If you have any question, let me know. Jesse, Christine. If not, I would like to say have a good night.
Have a good evening.
Bye-bye. Good night.
Bye.
Good night.
Good night.